In this video, we're going to discuss balanced reactions. So when we have chemicals react, let's look at CH4 and O2. So CH4 is methane, natural gas. So if you have a gas stove, gas heating, this is what you're burning. It reacts with O2, and we have an arrow to say, hey, these starting things that we put together, they go to make something else. They make carbon dioxide, and they make water. This is burning. This is the general products of burning. Whenever you burn wood or hydrocarbons, gasoline, oil, anything like that, you're generally producing carbon dioxide and water. So this is the idea of a reaction. We also call it a chemical equation. So at later times, you'll see it sort of just looks like math. I have x plus y equals z plus Q. And so if you do multiple reactions, you can actually link them together, treating it kind of like algebra. Not something we'll focus on too much at this point. What we do want to talk about, though, is what this represents in terms of the reaction. So when you light your stove on fire and the gas burns, the arrow is telling you you're doing that reaction. You've taken these two things, you're making them react and become these products. Until you spark that methane, it's not reacting, and you're just sitting over at starting materials. But once you do the reaction, they become products. So these are a few of the terms associated with a chemical reaction, or a chemical equation. Now this is a chemical equation. It is not a balanced chemical equation. For that, we have to recognize that there is a certain number of atoms that went into the reaction. I had 1 carbon, 4 hydrogens, and 2 oxygens. But if I look at my products, I have 1 carbon, 2 oxygen, oh wait, there's a 3rd oxygen, and 2 hydrogens instead of 4. I don't have the right number of atoms. You cannot create or destroy atoms doing chemical reactions. If you're the sun doing nuclear reactions, sure. But we are down here on Earth doing normal everyday Earth reactions. It is not possible to destroy your atoms. As a result, however many you put in, you must get out exactly the same number. So these atoms on both sides must be equal in number and type. Well, this raises a problem. Clearly, I don't have them being equal. How do we fix this? Well, think of it this way. If I had a reaction that said 1 frame plus tires goes to bicycle. Well, if you have a bike frame, how many tires do you need for that bike frame? Well, it's a bicycle. You need 2 tires. Things don't have to come in 1-to-1 ratios. You can need multiple of something to build your product, and this is true for atoms in a reaction. We need multiple of our starting materials, and we may make multiple of our products. So how do we go about identifying that? How do we find out how much we need of each thing? Let's go back and explore our starting reaction. The simplest way to go about balancing a reaction is to pick an element in only 1 molecule on each side. So first thing we do, well, oxygen is only in O2 on the starting materials, but it's in both of my products, so that doesn't work. But hey, carbon starts in CH4 and it's only in CO2 on the end. So we can start with carbon. So we'll say, all right, second step, change the number of the molecule so that element is same on both sides. What that means is, let's assume we have 1 methane. I have 1 CH4. Well, that means I have a single carbon. For every CH4 molecule, there's 1 carbon in it. So I have only one carbon on my left. I look over at my carbon dioxide and I say, well, each carbon dioxide has one carbon. So if I only had one carbon dioxide molecule, that would give me the same number of carbons on both sides. And so I've balanced my carbon atoms. They are now the same on both sides. Second step, pick another and repeat. Well, let's look at hydrogen. Hydrogen's on only one molecule on both sides, and I've already set how many hydrogens are on my left. Because I said I'm only going to have one of these so that my carbons are one, I have to only have one of them for the hydrogens as well. And so I have 4 hydrogens on my left, on my starting materials. Way over here, my waters, well, each has 2 hydrogens, so I need a total of 4 hydrogens. I can't change the formula, it wouldn't be water anymore, but I could just have 2 waters. Each water, so there's an H2O and another H2O, for a total of 4 hydrogens. By having multiple waters as a product, I can have the 4 hydrogens on both sides. At this point, I only have a single molecule left to adjust. Now, dioxygen contains oxygen, and oxygen atoms show up on both products, but we've already set how much of those we need. So we really only have one molecule that hasn't been adjusted. And so I can take my oxygen now and say, hey, I know from my right side that there's 2 oxygens for my CO2, and from each water there's 1, so there's 2 oxygens from my waters, for a total of 4 oxygens on the right side. The only way to get those on the left is dioxygen, so I need 4 total. I must have 2 dioxygens. Each dioxygen has 2 oxygens. If I have 2 of them, that's 4 total oxygens. What we've done is we have balanced this reaction. For every 1 methane molecule that burns, I need 2 dioxygen molecules. They'll react, the atoms will break apart, reorganize, they will produce a single carbon dioxide and 2 waters. This is how we balance a reaction. Let's try it again. We'll continue with the carbon. Let's do C3H8 plus O2 goes to CO2 plus water. Give this one a try. Go ahead and pause. See if you can balance this one and then come on back. All right. Well, if we want to try, first we have our C3H8. This is propane. If you use a gas grill outside, this is the gas you are burning. Well, I have 3 carbons. Let's assume I use one of this molecule. That's going to give me 3 carbons on my left. I need 3 carbons over on my right. They come from carbon dioxide, which only has 1. So I'm going to need 3 carbon dioxides to get those 3 carbons. Next, hydrogens again. Well, because I set my left hydrogens at 8, a single propane contains 8. There are 8 hydrogens on the left. I need 8 hydrogens on the right. At the moment, I only have 2. Well, the only way to get more is to have more of that molecule. So 4 waters, 4 times 2 is 8. And so I can get 8 hydrogens if I have 4 waters. Last step then, well, oxygen is left over. 3 times 2 for 6 oxygens from my carbon dioxides. 4 times 1 for 4 oxygens from my water, for a total of 10 oxygen on my product side. So I need 10 oxygen on my reactants, on my starting materials, and they come in pairs of 2. So 5 times 2 will give me 10. The balance reaction for propane burning is that for every 1 propane, you need 5 dioxygen molecules. You make 3 carbon dioxide and 4 water. Let's show a specialty case. If we do C2H6 plus O2, CO2 and water. So we'll keep the reaction more or less similar. In this case, however, if I assume 1 ethane, well, that's going to give me 2 carbons, so I'd need 2 carbon dioxides. It's going to give me 6 hydrogens, which would mean 2 times 3 will give me 6 hydrogens over my products. But if I go to do my oxygens here, well, 2 times 2 for 4 oxygens from carbon dioxide, 3 times 1 for 3 oxygen for a total of 7 oxygen. Well, if I need 7 oxygen, then I would need 3.5 dioxygens. Problem is, you can't do that. You can't have half of a molecule. Atoms can't be cut. If you break a molecule in half, it's not the same molecule. We cannot have fractions of a molecule. So only way to fix this is, well, you can get rid of a half if you double it. And so this becomes 7. All the others double. And so what we really find is that it is 2 C2H6s for every 7 dioxygens, produce 4 carbon dioxides and 6 waters. Now if we check real quick, 2 times 2 is 4 carbons on the left, 4 times 1 is 4 carbons on the right. 2 times 6 is 12 hydrogens over on the left. 6 times 2 is 12 hydrogens over on the right. 4 times 2 is 8 oxygens plus 6 for a total of 14. And 7 times 2 is 14 oxygens. Sometimes you have to double or possibly even triple your entire formula in order to get rid of a fraction. This is simply, again, because we cannot have half a molecule or a third of a molecule. And so we write them as whole numbers. What's the lowest whole number mix for that reaction? Here's another practice problem. This is iron 3 oxide and aluminum. So rust and aluminum. If anybody's ever watched Mythbusters and like, this is thermite. They used a lot of it in that show for fun. Thermite is amazing. You take rust and aluminum, you finely powder them, you mix them together, you light them on fire. The aluminum wants those oxygens so badly that it rips them off of the rust, turning the rust back into regular iron, but also so hot that it is molten iron at the time. So this is what they used to do for it is if you had train tracks, and so you'd have the train ties, and then they'd be at the end. And so you'd have one rail, and then you'd have another rail. Well, the problem is they're not connected. And so they would fill it in with thermite, put some sand around it on both sides, light it on fire, and then as it melted, it would burn into and melt and weld itself to the other train ties. And so in the end, you would just get one continuous piece of iron. And so there's parts of this country where, they did this for miles and miles and miles before there was any interruption in the track. So there are pieces of iron that are dozens, if not 100 miles long, one continuous chunk, because they've been welded together. So fun use for thermite. In our purposes, though, go ahead, pause this, and see if you can't balance this reaction. All right, if you're back, well, different atoms, but let's pick something that's on one thing on both sides. Let's go with aluminum. I have 1 aluminum over on my left. I have 2 aluminums on my right, so I'm going to need more aluminums on my left. In fact, I'll need 2 of them. Well, this sets my oxygens over on the right. If I have a single Al2O3, that means I have 3 oxygens. And so the only option is, well, I need 3 oxygens on my other, and there is already 3 oxygens. So I must have only 1 of my rust. Well, that's going to set my irons at 2, which means way over here on the right, my free floating iron with only just on its own, I need 2 of it. Now, be very careful. This is not Fe2. That subscript tells us it is a pair, that it is a molecule that specifically comes as 2. That is not the case. Iron in the formula is just a free atom. It's a chunk of metal. And so it needs multiple of the irons, but they are free and independent of each other. They don't have to come as a pair. So this symbol out front, it actually has a term. It is the coefficient. It is not part of the molecular formula. It is a number out front that tells us how many of that formula we need to balance the reaction. It's like saying you need 2 tires. You don't weld your 2 tires into a single thing. I mean, if you try to hook your bike up where you have your 2 tires taped together and then your frame, handlebars, and an empty set on the back with nothing, that doesn't really work. Okay, pedals. There you go. Like, this is not going to work. You can't merge 2 independent things into one thing. So you need to keep that 2 out front to tell you, no, it's really 2 separate things. Coefficients, finding them for balanced reactions is the key to being able to figure out how many of each molecule is actually necessary for that reaction to occur.